Hi everyone. I thought we'd do a little review of where we've been the last couple of days with these problems involving garden gnomes and my gnomes and my garden. The population of gnomes in my garden grows exponentially. The initial population of gnomes was 7, and after 3 years the population was 12. So we've got initially 7, and after 3 years our population was 12. Find the growth rate for the gnome population. That's part A. B, how many gnomes are there after 10 years? And C, when will there be 100 gnomes in my garden? Okay, let's see. First, I think we need to build a model. So, A equals P e to the RT. And we'll plug in our initial quantity for P. A equals 7 e to the RT. And then I'll plug in this ordered pair for T and A. 12 equals 7e to the r times 3. Okay, I need to get this exponential by itself, so I'm going to divide both sides by 7. Over here I'll have e to the 3r, and on the left side of the equation, 12 divided by 7 is 1.714 to a 5714. So now I need to take the ln of both sides. So I can bring this power down in front. ln 1.714 to 85714 equals 3r. ln of e, remember the ln of e is 1, so we don't need to be worried about that anymore. We just need to divide both sides by 3 to get r by itself. So if I take the ln of this number, and then I divide that number by 3, I end up with a rate of 0.17966550002. Okay, so what would my model be then? Well, when I put it back in, I'll have A equals 7e to the 0.17966550002 t. Part A said, find the growth rate of the gnome population. Well, I can see it's approximately 18%, 17.966 or 967%. There's part A. There's part A. I'm using my rate to tell me the growth rate. Okay, part B, how many gnomes are there after 10 years? Is 10 years an A value or a T value? Remember, we plug time into this function and get a number of gnomes out. Since they've given me 10 years, I want to plug a 10 in for time. So for part B, A equals 7e to the 0.17966550002 times 10. And then I'll ask my calculator to help with that. I'll multiply the rate by 10. I'll do e raised to that power. And I'll multiply that result by 7. And I get that A equals 42.206 gnomes. Okay? And part C says, when will there be 100 gnomes in my garden? Well, 100 gnomes is not a time, it's an amount of gnomes, so I'm going to plug 100 in over here and set that equal to my model, 0.17966550002t, and I want to solve this equation for t. So the first thing we're going to do is divide both sides by 7. So that'll give me 100 over 7 equals e to the 0.17966550002t. And then, what do we need to do? We need to take the ln of both sides and bring this down. So we're going to have ln of 100 divided by 7 is 14.28571429. And over here, we'll bring the power down and have 0.17966550002t. Well, it looks like all I need to do now is divide both sides by my rate, 0.17966550002. to get t by itself. All right, so ln of 14.28571429 and divide that by 0.17966550002. I get that t equals 14.801 years. Okay, there's our first problem. We had to build a model given these 2 points. That's very common for us in our class. And then we had to determine the growth rate. That's what we were solving for originally, solving for that r value. And then we plugged the growth rate back in with our original amount to build our model. We used our model by plugging 10 in for time to find out how many gnomes we'd have after 10 years. And in part C, we wanted to know when we would have 100 gnomes, so we plugged 100 in for A and solved for T by first dividing and then taking the ln of both sides and dividing both sides by our rate. Okay, let's move on. Okay, the second problem I want to look at, dealing with my garden gnomes. When a gnome dies, he decays radioactively. A cat wanders into my garden and kills a gnome, but in the true cat fashion, it just killed it for fun, never intending to eat it. The gnome is left to decay. The half-life of a gnome is 15 days. Dead gnome originally weighed 22 pounds. How much of the gnome is remaining after 3 weeks? And when will there only be 5 pounds of gnome remaining? All right, well, let's take a look at our givens. We're given here the half-life of a gnome is 15 days. Half-life is 15 days. That's the time it takes us to have half of the original amount. Using the shortcut we talked about yesterday, we know that k, or r, is ln of a half over 15. So when I go and build my model, using a equals p e to the rt, the initial amount, the initial gnome weight was 22 pounds, and my rate is ln of a half over 15. Don't forget that t. So here's our model. First question, how much of the gnome is remaining after 3 weeks? Well, 3 weeks is how many days? That's 21 days. So I want to know the amount after 21 days, which means I want to plug in a 21 for t. ln of a half over 15 times 21. Okay, well, this is all done on the calculator now. On the calculator, I'm going to do ln of a half divided by, let me see, ln of a half divided by 15 times my 21 years. I want e raised to that power, and I want to multiply that result by the original 22-pound gnome weight. So after 21 days, the gnome carcass remains will be 8.336 pounds. Not much gnome left. Okay, next question is, when will there be only 5 pounds of gnome remaining? So 5 is an amount. I'm going to plug that in on the left side of the equation and set my model equal to it. ln of a half over 15 times t. So I need to solve for this t up here. Okay, first thing I'll do is divide both sides by 22. I'll get 5 divided by 22, which is 0.22727272773. And on the left-hand side, I'll have e to the ln of a half over 15t. I know, you could certainly decimalize this, but we're about to take the ln of both sides and bring this down, so I'm just going to do that. ln of 0.227272773 equals ln of a half over 15t. Well, I want to get t by itself. If I multiply both sides by 15, these cancel. And if I divide both sides by ln of a half, these cancel. So I want 15 ln of 0.227272773, and I want to divide that by ln of a half. I end up with t equals 32.063, and these are days, remember. 32 days until there will only be 5 pounds of gnome left. Okay, what's next? Well, next, I want to deal with a different type of question, and that's the question of reasonableness. These exponential models that we've been using, especially the ones for population growth, suggest something about population over time. So if I see something like a equals 10e to the 0.2t, we know that this is an exponential growth model. We know the initial amount. We could even sketch a quick graph. Y equals 0. If I plug a 0 in here, e to the 0 is 1. 1 times 10 is 10. Where is this function going over time? To what value will the amount head? Well, this is exponential growth. It grows forever. Is it possible for populations to grow forever? I mean, think about it. Can the number of people on this planet become infinity? Can the number of bacteria in a sponge be infinitely large? It turns out the answer to these questions is no. Populations always have a maximum called the carrying capacity of the environment. So because environments have carrying capacities and populations can't grow forever, we need a new type of model. I'd like to introduce you to this new model today. It's called a logistic model. It was mentioned in section 3.3, I think it was, in one of the matching activities. And a logistic function comes in a form that looks like this. F of x equals 12 over, well, let's start with the general case. I'm sorry. Here's the one I wanted to show you. Okay. So here's what I know about logistic models. First of all, they have two horizontal asymptotes, one at 0 and one at, this says y equals L. Well, what's L? It's this number up here in the numerator. This is my general logistic model. And no, you won't be building logistic models and writing the equations for them unless you're a real glutton for punishment. In our class, mostly we'll be just working with given logistic models. But what we do know is that this logistic model has horizontal asymptotes at y equals 0 and y equals L. The y-intercept we get by plugging a 0 in for t. Well, e to the 0 is 1, and 1 times c is c, so we end up with L over 1 plus c as the y-intercept. I wouldn't bother memorizing that. I would just plug a 0 in for t each time to find the y-intercept. The domain is all real numbers. There's no restriction here. And of course, the range only goes from 0 to L, the carrying capacity of the environment. This function is always increasing. It's concave up and then it's concave down. And curiously, the point where the function changes from concave up to concave down, this is the place where the growth rate is fastest. This point has a y value of L over 2. Now that's not the x value, that's the y value. So if I graphed the line y equals 2 and I graphed my logistic function and did second calculate intersect, I could find that point where the growth rate was fastest or where the function changed from concave up to concave down. Okay, so what are we going to be doing with logistic functions? Well, let's take a look at the sample problem. I'd like to do some of the algebra basics before we actually get into the word problem. I've got a function here, f of x equals 12 over 1 plus 2e to the negative 0.1x. And I want to know f of 0. Well, to find f of 0, I'm going to plug a 0 in for the x's. That's going to give me 12 over 1 plus 2e to the 0, which is 12 over 1 plus 2, or 4. So I know the y-intercept for this function is going to be 4. Okay? Let's take a look at f of 1,000. That's a pretty big number. 12 over 1 plus 2e to the negative 0.1 times 1,000. Well, that's going to be 12 over 1 plus 2e to the negative 100. Well, let's think about this for a minute. Before we reach for our calculators, let's think about it in these terms. This is a negative exponent. And if I look at e to the negative 100, that's the same as 1 over e to the 100. Imagine one pizza and e to the 100 people coming for dinner. What's that going to be? Well, it's not exactly, but it's awfully approximately 0. So this is going to become 0. 0 times 2, 0, plus 1 is 1. So for all intents and purposes, I get 12 over 1, or 12. Now it's not exactly 12, and if I actually put in that e to the negative 100 in a calculator, I wonder what my calculator gives me. Let's see. E to the negative 100. Ugh. All right, and I want to multiply that times 2, and I want to add 1 to that. Oh, well look, my calculator says that when I add 1 plus 7.4 times 10 to the negative 44th, I'm really getting something pretty close to 1. So this is all but 0 over here, and so this all becomes 0, and so my denominator just becomes 1, and so I end up with 12. Well, what that tells me is, as I plug in bigger and bigger numbers here, this function is heading towards a value of 12. And lo and behold, 12 is the carrying capacity of the environment. Now, we don't actually get to 12, but boy, we get awfully close to 12. Okay, so can we sketch a quick graph of this? Well, we said that there was a y-intercept at 4 and a horizontal asymptote at 12. Zero, 4. And this up here is y equals 12. And like I said, if you want to find this point here, where we go from concave up to concave down, we know the y value here is half of this. So we know the y value here is 6. If I take out my calculator and I graph these two things, clear, y equals 6 and y equals 12 divided by, remember, everything in the denominator has to be in parentheses, negative 0.1 x close two parentheses. Okay, and I want to change my viewing window so that the y min is 0 and the y max is 12. And I want my x's to go from 0 to 10 and graph. So here we see this logistic curve growing up. Here we see the line y equals 6. And if we do second calculate intersect, we see that when x equals, no, I didn't do second calculate intersect. Okay, first curve, yes. Second curve, yes. Guess, no. There we go. The y value is 6, and the point of intersection is 6.931. So this would be 6.931. Those of you moving on to calculus, that point is going to be important for next year. For this year, you don't have to worry so much about this. Okay, any questions about the basics? Let's move on now to solving with logistic. Okay, so let's say I have the equation f of x equals, oh, you know what? We just set the equation equal to 6, didn't we? Why don't we do this algebraically and see that we can also get that 6.931 value. Okay, so 6 equals 12 over 1 plus 2 e to the negative 0.1x. Well, the first thing I'm going to do here is multiply both sides by the denominator. That'll allow me to cancel. And I'm not going to distribute. I'm actually going to divide both sides by 6. So these will cancel, and I'll have 1 plus 2 e to the negative 0.1x equals 12 over 6, or 2. Then I'm going to subtract 1, so I'll have 2e to the negative 0.1x equals 1. I'll divide by 2. And now I've got e to the negative 0.1x equals 1/2. Well, what do I need to do now? I need to take the ln of both sides. So I can bring this power down in front. So I'm going to have negative 0.1x equals ln of 1/2. And if I divide both sides by negative 0.1, and then pull out my calculator and do ln of 1/2 divided by negative 0.1, I get 6.931. So we didn't even really need to find this point of intersection graphically. We could certainly do it algebraically. I just think it's a lot faster to do it graphically. Okay, so now what are we going to do with this logistic stuff? Well, I have two logistic problems involving cats and gnomes that I'd like to look at with you. Okay, here's the first one. First one says, if the population of cats in my gnome garden grows according to this logistic behavior model below, where t is measured in weeks, how many cats can my garden support? What's the carrying capacity of the garden? Well, we know the carrying capacity is this number on top, so we know the answer to the first question would be the garden can support 84 cats. That's a lot of cats. I really don't recommend that. Okay, B, what's the growth rate? Well, I see a growth rate here of 0.07. And you say, but that's a negative in front of that. Isn't that decay? Well, not really. Not with logistics. And I don't really want to get into that here. Instead, I'm just going to jump on now to what was the initial population of cats. Well, we talked about this, and we said that if we plugged in a 0 for t, we would find our initial population. Well, e to the 0 is 1. 1 times 11 is 11. 11 plus 1 is 12. And so we end up with 84 over 12, which is 7. Originally, there were 7 cats. Okay? And how many cats are present after 5 weeks? Well, remember they told us that time was measured in weeks here. And so to find out how many cats there will be after 5 weeks, all we need to do is plug a 5 in for t here. So what do I get? Pull out my calculator, a little trusty calculator, and I've got 84 divided by 1 plus 11 e to the negative 0.07 times 5 weeks. And I have to close a second parenthesis. Second, yes. Okay, it looks like 9.598 cats after 5 weeks. You can certainly write down on your homework or test 9.598, and then if you like, approximately 10 cats. But I definitely need to see the 3 decimal place rounding showing up here. Okay? So there's my first logistic question for you. Second logistic question for you. The growing population of cats in the gnome garden forced the gnomes to migrate to the attic. So now the population of gnomes in my attic grows according to this logistic model, where t is measured not in weeks, but now in days. How many gnomes can the attic support? Again, that's the carrying capacity of the environment, or 110. What is the initial population of gnomes in my attic? Well, for that, I'm going to have to plug a 0 in for t. E to the 0 is 1. 1 times 27.3 is 27.3. Plus 1 is 28.3. And so I want 110 divided by 28.3. And I get 3.8869 gnomes. That's 110 divided by 28.3. Okay, next we've got how many gnomes are present after a fortnight. Well, a fortnight is 2 weeks, or 14 days. So I'm going to plug a 14 in for time here, because time is measured in days in this problem. So 14 times negative 0.14 e raised to that power times 11. Ooh, no, that was the last problem. That was cats. Times 27.3 plus 1. That's my denominator. And now I want 110 divided by that number. And I get there will be 22.702 gnomes after 2 weeks. So we started off with 3.8869 gnomes. And we know that we can support a total of 110, but right now we've only got 22 gnomes, so plenty of room for more gnomes. And then the last question, when will there be 72 gnomes in my attic? Well, let's take a look at that. 72 gnomes. So 72 equals 110 over 1 plus 27.3 e to the negative 0.14 t. And I'd like to solve this equation. Okay? As we've been doing since August, when we have a fraction in an equation situation, I'm going to multiply both sides by the denominator to clear out that fraction. I'm going to do that over here as well, but I don't really have enough space, so I'm not going to force it. And I'll just know that that's over there. So now 1 plus 27.3 e to the negative 0.14 t times 72 equals 110. Now, I'm not going to distribute here. You can, but 72 times this is going to be a big number. And instead, I find my life is made easier if I just divide both sides by 72. So I'll get 1 plus 27.3 e to the negative 0.14 t equals, and 110 divided by 72 is 1.527777778. Okay, I need to subtract 1 from both sides. So 27.3 e to the negative 0.14t equals 0.527777778. And then I'm going to divide by 27.3 to clear out this, to get that exponential by itself. And that gives me e to the negative 0.14t equals 0.0193325,193. If I then take the ln of both sides, I can bring this down in front and have negative 0.14t equals ln 0.0193325,193. And if I divide by negative 0.14, I'll find out the time. So ln of that number divided by negative 0.14 gives me approximately 28.185 days. After 28 days, a little more than 28 days, we'll have 72 gnomes in the attic. Okay, I think that should be enough information for you to do the in-class worksheet on logistic models, and you certainly have had enough practice to do the homework worksheet assignment number 10. Don't forget to send me any group me questions, and I hope the lag on this video isn't atrocious. All right, take care. Oh, and happy Thanksgiving, everyone.